Hello everyone, this is Dr. Young, and in this video we're going to talk about the Bohr model. We're going to start our discussions about quantized energy, kind of what the Bohr model is, and then we'll talk about some of the disadvantages of it and why the model needed to be refined and eventually thrown out. In the video following this, we'll talk more about electrons as waves and the Heisenberg uncertainty principle a little bit before we jump into actual quantum numbers and everything. So remember here, right, in the previous videos, if you haven't watched them yet, you really should. We talked about how light is sort of bizarre and that it has wave-like properties like diffraction, and that kind of helped us figure out some interesting things about atomic absorption and emission spectra. And there are these very specific wavelengths of light that were either emitted or absorbed by different elements. And so what we're going to talk about now is this idea of quantized energy levels and talk about and relate that to the actual Bohr atom itself. So about 1900 or so, a man named Max Planck proposed a sort of radical new way to think about energy. Instead of energy as having any sort of allowable value, he proposed that energy was quantized, which meant that it could only come in discrete packets. And so he's saying that energy values could have like it could be at a certain level, or another certain level, or another certain level, but that you couldn't have values in between those levels. He came up with this concept of having energy come in discrete little packets, in chunks. And what he was saying was that it's not like a ramp, it's more like stairs, right? So it used to be thought of, well, you could just have energy come in chunks, or sorry, not in chunks, in any allowable amount, like a ramp. You just have this value or this value or this value, like any sort of amount, versus this sort of like stair-like concept where, again, there were discrete amounts of energy that were allowable. And this idea may not come as a huge surprise given that Max Planck was a really good pianist, supposedly. He was a great musician, was going to become a pianist and decided to go into science, luckily for us. But it's kind of like with piano keys, right, where your notes are in discrete amounts, right? You can have this note, or you can have this note, or that note, or that note, or that note, but there's no key for in between those notes, right? You have to just kind of go up and down your scales, but there's nothing in between the two. So that music, the note comes in discrete amounts. And right, if you take a look at a score of music, your notes can be here, or here, or here, or here, but they're going to be somewhere right on these lines or in the middle of these lines. We don't really have, or at least in Western music, right? We have octets and nothing really beyond that, no sounds in between the sounds. And so he's proposing that energy is kind of like this, that you could have, right, like a C note or an A note or a B note, but there's nothing in between that A and the B note, even though, we have sharp. Ignore the whole sharps and flats thing. Just follow me here, right? That when you press your fingers on a key, it's a certain amount. He said that energy is that way too. And so what he found was that he came up with this constant here, looking at a bunch of different data. We don't need to get into it, but something that we now call Planck's constant, which is this H here. This became Planck's constant. And it has a value of 6.626 times 10 to the 24, or sorry, negative 34th joule seconds. And this is sort of what he said that the energy would come in packets of, that this helped you relate things like, for example, frequency of light to the energy of that light. Right, so if you want to know the energy of light, the allowable values for the energy of light depended on the frequency and Planck's constant. We can rearrange this if we take the speed of light equation, right, where we have the speed of light, which is c equals the lambda, which was the wavelength, times the frequency, nu, so lambda nu. If you rearrange that and substitute it in, you get this very important equation. This is big time stuff. We're going to use this quite a bit for this chapter, right, where he's saying that the energy of a photon depended on his constant, Planck's constant, which again is just 6.626 times 10 to the negative 34th joule seconds. The speed of light, which we're going to say is 3.00 times 10 to the 8th meters per second. and then the wavelength, right? Whatever the wavelength is here. Not wave number, wavelength. And this would be in meters, so that our units make sense here. So that would be in meters. So we can use this equation to figure out the energy of a photon at a given length. So if someone asks you, right, what's the energy of a red photon that has a wavelength of 740 nanometers, you can just plug it into this equation. You can say, oh, well, I know that the energy equals Planck's constant times the speed of light divided by the wavelength. And so therefore I have 6.626 times 10 to the negative 34th joule seconds divided, and then times, I guess, times 3.00 times 10 to the 8th meters per second for my speed, or for the speed of light, and then divide that by the wavelength in meters. So that would be 7.40 times 10 to the negative 7th meters, right? If you convert nanometers into meters here. And then you just pop that into your calculator, and out comes 2.69 times 10 to the negative 19th joules. Right, so that's how much energy that one photon would have at 740 nanometers. And you could do this for visible light. You could do this for anywhere in the spectrum, whether it's gamma radiation, or if it's radio waves or infrared or anything like that. You can use this equation, Planck's equation, to figure out the energy and how it relates to the wavelength of a photon of light. Now, the concept that the energy and the wavelength are related was really important when you're looking at things like atomic spectroscopy, right? We talked before about how you have these, like you're just looking at hydrogen. Hydrogen emits at 4 different spots, 4 different wavelengths, but that means it corresponds to 4 different energies, right? These 4 photons have 4 different energies. Higher energy for the purple one, lower energy for the red one, right? Because smaller wavelengths are higher energy, longer wavelengths are lower energy. And a man named Niels Bohr looked at these spectra, and he proposed a model of the atom that involved what the electrons look like. Basically, in a nutshell, he proposed what's called the planetary model, where you had the nucleus, right? They knew that the nucleus was a small hard center now, thanks to Rutherford and those folks. But he proposed that what happened is that the electrons, and I'll draw this in red here, he said that the electrons basically just kind of like orbited around the center nucleus. So he said you'd have these electrons in these orbitals, and they would just basically spin round and round and round, which models, right, a solar system, a planetary model. So it looks something like this, where the nucleus was kind of like the sun in the solar system, and then the electrons were a lot like the planets that would go around the sun, right, thanks to gravity. So he thought that, well, maybe that what we see in our universe is a lot like what we see in the subatomic universe. So what he did is he said, okay, so here's how this works. He said that, okay, well, first of all, I'm just going to point out the energies here, right? I calculated how many joules there are for that purple absorption and that blue absorption, and I don't really have a good turquoise. Well, let's just use green. And then for the red absorption, right? So there's 4 different absorptions. He said that the reason that this works, like how this works, he said, okay, well, let's say you have an electron here, right? You have an electron. And what happens is that a photon of light is going to come in, right? Let's say a red photon comes in and hits this one, right? That apparently has something like 303 times 10 to the negative 19th joules. He said that what happens to that photon is that photon is then going to get promoted and jump up into a new orbital. So when light gets absorbed, the idea is that you promote an electron into a higher energy orbital. right? So that would be going from left to right. So he's saying that now instead of in that innermost orbital, now the electron is in the second innermost, right? So it got promoted up a level, right? And let's just call this 1, 2, 3, and this 1, 2, and 3. So it went from level 1 up to level 2. That promoted the electron. And that's what happened to this photon, right? So when this photon got absorbed by this element, and you say this is hydrogen, then it popped up, and that's why we see this little black spot right here, because that photon gets absorbed by promoting an electron, to getting that electron to go up into a level. And promoting electron, I should underline that or something. To promote an electron, that's a very common verbiage. Promote an electron means for it to go to a lower energy level to a higher energy level. And he said that this would just correspond to, right? So having, again, different energy levels. He's saying, well, we're going to have that little electron friend down here. And again, this is just another way to draw it, that it's going to get promoted up to here when that red light hits it. And so he's saying, well, now afterwards, the electron is up here, it's at that higher energy level now, right? So we've promoted it to a higher energy orbital, which corresponds to a higher energy value. And that's fine for the absorption, right? How maybe it absorbs. And then, so the idea is that there's different colors here, because you could absorb, maybe you got hit by a purple, a higher energy photon instead. And so then maybe your electron was able to jump to an even further orbital. And it got even more promoted, and it went to an even higher energy level. So he's saying that the reason why we have these different bands is because they're different electronic transitions, that you jump from one level to a different level, and that there's lots of different possibilities, and the more complicated of an atom you get, the more possibilities there are, which is why some look more complicated than others. Now, the opposite of this would be relaxation. So the idea is that you have this orbital, you have this electron here that's at a high energy orbital. What it can do is it can then fall back down to where it was, right? So it's going to go back down to where it was. But in doing that, it spits out that red photon again. So it creates a red photon of the same energy as the one that promoted it. That this difference here, that this difference between the first energy level and the second energy level corresponds to the energy of that photon. So if you jump back down, that's called a relaxation, that's going backwards. So light is emitted. So light is emitted when an electron relaxes. When an electron relaxes back to the ground state. Back to the ground state. So some more terms for you. This first part where the electron is closest to the nucleus, that's called the ground state. When it gets promoted up to a higher energy level, that's called the excited state. So you could draw the excited state with these rings, or you could draw it as this energy diagram where you have an electron at a higher energy level. Same thing for the ground state. You could draw it like this, where you have the electron closer to the nucleus, or you could draw an energy diagram where you have the electron at the lower level. So Bohr was proposing this as an explanation for these absorption and emission spectra. He's saying, well, that's why you absorb light, is because you can promote electrons in different combinations, so you get different absorptions, right? Or you can have an electron relax, which is going to emit light, which is why in the emission spectra you see just that band show up. And it's also why the emission and the absorption are similar, is because they have the same values. Let me write that too, the same delta E, right? That the difference in energy when you jump up right? This difference in energy right here, when you jump up, that absorbed a certain wavelength of light. And this difference in energy right here is the exact same as before. And so that's why you emit a photon of the same value, of the same energy level, of the same wavelength. Right? So here's just another drawing of two different atoms, right? Two different elements. Helium is clearly more complicated than hydrogen is. And he said, oh, well, that's fine. That's totally fine, because what we have here is we have an electron. If I look at an electron here and here, these are going to have different delta E values, right? This gap in energy is smaller than this gap in energy. And so it makes sense that they would absorb or emit at different spots, right? That they wouldn't match is because different atoms have different sizes. They're going to have different numbers of electrons, and so these values are going to be different. And so you said, oh, okay, well, yeah, if you look at, and if you just look at sort of like an energy diagram here, yeah, this one's going to have a level that looks like this, and so you're going to promote an electron right from here to here. And they're going to have that corresponding electron having moved up if you absorb. But this one, since it's bigger, it's going to have a different sized gap. And so your difference in energy is going to be larger. Right? So you have the energy gap here is going to be smaller, less energy. And this would be more like a red photon, right? Because it's a lower energy, longer wavelength. Versus over here, this is going to be a larger delta E gap, which means it's going to be a shorter wavelength and more of a purple, more of a violet. And right, I'm not asking you to be able to like look at an atom and predict what colors might come out of it, but I just want you to have a sense of what Bohr was trying to get at. He's saying that you have a central nucleus, that you have these electrons orbiting that nucleus, and that light can make those electrons jump from orbital to orbital. And the further away from the nucleus they get, the higher energy that it's considered, and that requires light, and it's going to absorb that photon. Then when those electrons drop back down from those orbitals and get closer to the nucleus, that releases energy in the form of light, and which is why we see those emission. So now this model had some issues. It worked okay for like hydrogen, but as soon as you got more complicated atoms, it just kind of all went to pot. But it really got people thinking in the right direction. And honestly, the Bohr model is really, really great and really useful for lots and lots of different applications. But it turns out that it got ditched pretty quickly for quantum mechanics. And so that's what we're going to talk about next, right? So in our next video, we're going to talk about electrons as standing waves, so that we can then eventually get to this idea of wave functions, right? So again, to kind of reiterate, light was weird. It diffracted. People used prisms. They're just trying to make little cool rainbows. And then they realized that if they shined the light that's emitted from an element, that when they tried to look at that whole spectrum, they only saw these little lines. And so someone was like, hey, maybe there's only little lines because only certain energy values are allowed. And Bohr was like, yes, that's because everything looks like tiny planets. Awesome. That's why there's only certain energies allowed, because they have to get from one ring to another ring, nothing in between. And so now we got to talk about electrons not really being particles, kind of being like waves, and then things start to get really, really weird. So hopefully that gives you a little better sense of what the Bohr model is kind of like. But again, we're going to kind of ditch it almost immediately to start talking about quantum mechanics.